All right, let's dive into one of the most fundamental building blocks in all of computer science. It's a concept that is all about order, fairness, and, as you'll see, the simple power of patience, the queue.
I mean, think about it. You've definitely done this. Waiting for your morning coffee, lining up for a movie, you get in line, and you wait your turn. It's just a basic, everyday rule of life, right? Well, believe it or not, that exact same simple rule, first person in, first person out, is the engine that powers some of the most critical and complex systems we rely on every single day. We're talking everything from your computer's operating system to the massive web servers that are delivering this to you right now. And that brings us right to the heart of what a queue is all about. This principle has an official name, and it's super intuitive. It's called first in, first out, or, as you'll always hear it, FIFO. And FIFO means, well, exactly what it sounds like. The very first item that joins the queue is always the very first item to leave it. There's no skipping the line here, no cutting in. It's this strict, predictable order that makes queues so incredibly useful and powerful. Okay, so how do we actually use a queue? It all boils down to two fundamental operations, two main moves that everything else is built on, NQ and DQ. Let's walk through it. When a new item shows up, it performs an NQ, which just means it gets in line at the very back, what we call the rear of the queue. Now, if we just want to see who's next without actually letting them go, that's called a peek. And finally, when it's time for the person at the front to be served, they get DQ'd. That's really it. You add to the back, and you remove from the front. Simple. And this is where the magic happens. Both of those core actions, adding an item and removing an item, are incredibly, ridiculously fast. In computer science terms, we call this constant time, or O1. What that really means is that it doesn't matter if there are 10 items in the queue or 10 million items in the queue, the operation takes the exact same tiny amount of time. This kind of predictable, lightning-fast performance is precisely why queues are used to build systems that need to scale up to massive sizes. So, we know the rules of the game, but let's peek under the hood for a second. How do programmers actually build these things? Well, there are two main ways to go about it, and each one has its own set of trade-offs. So, on one hand, you can use a basic array. Just think of it like a line with a fixed number of spots painted on the ground. It's really fast and very efficient with how it uses memory. The other way is with a linked list. This is more like a conga line, where each person just knows who the next person is. It's super flexible because the line can just keep growing forever if it needs to.
So how do they really stack up? Well, they're both incredibly fast at their main job of adding and removing things. But the array often gets a little performance bump because all its data is stored together, which computer processors really like. The linked list needs a tiny bit more memory for each item to store those links in the chain, but its killer feature is that flexibility. It can grow as big as you need it to be. Now, to handle the issue of running out of space in an array, programmers came up with a really clever trick, the circular queue. Instead of just stopping at the end of the array, the queue just wraps around to the beginning, reusing any empty spots left by items that have already been served. It's a seriously elegant solution that makes array-based queues super efficient.
Okay, this is all great in theory, but where does this stuff actually show up? Well, it turns out queues are the silent workhorses behind a huge part of our digital lives.
Have you ever sent like 5 different documents to the printer all at once? They don't come out all mixed up and jumbled. That's because a queue, called a print spooler, lines them up in the exact order you sent them. First document in, first document out. It's a perfect, simple example of FIFO in the real world.
Or what about when thousands or even millions of people are all trying to get to a popular website at the same time? The server doesn't just panic and crash. It uses a queue to handle every single one of those incoming requests in a fair, orderly line. Your request literally gets in line and is processed when it's your turn.
It goes even deeper than that. Right inside the brain of your computer, the operating system is using queues to decide which programs get to use the processor. Every application gets into a ready queue and waits for its little slice of CPU time. This is what makes your computer feel so responsive, even when you've got a million things running at once.
Now, to really lock in what makes a queue so special, it's super helpful to compare it to its famous cousin, the stack. They're both ways of organizing data in a line, but they operate on completely opposite principles. This is my absolute favorite way to picture it. A queue is a line of people. It's fair, it's orderly, first come, first served. A stack, though, is like a stack of plates at a buffet. You put a clean plate on top, and the very next person takes that same plate right off the top. So the last one in is the first one out, or LIFO. This one single difference in ordering means they're used for completely different things. So, what are the big things to remember here? First, queues are all about that strict first in, first out order. Second, their main jobs, NQ and DQ, are ridiculously fast, O of one time. Third, you can build them with arrays if you need raw speed, or linked lists if you need flexibility. And finally, they are absolutely essential for scheduling, buffering, and managing requests pretty much everywhere in computing. But all this talk about fairness leaves us with one last, really interesting question. What happens when the line isn't supposed to be fair? I mean, what if some items in the line are way more important than others? An emergency room doesn't work on a first come, first served basis, right? For situations like that, we need a special kind of queue, and that's exactly what we're going to dive into next time, the priority queue.